Okay, so we solved the homework last time. Did we start talking about compression yet? We didn't start talking about it yet, right?
Well, we talked about the concept, but not the actual.
I mean, did we do like math with like high definition TV and stuff like that? We started doing that, right? Kind of like, here's the reason why compression makes sense, even with today's high-speed internet connections and stuff like that. You know, even if you had the fastest, internet that's out there today, gigabit internet, let's say, which is 128 megabytes per second download speed. Even then, if you wanted to stream a full high definition channel, it's a lot of whatever we came out with the math for it, but a lot of data. Do I actually have the, oh, here it is. Yeah. So we decided that for full HD, we would need for 1 single second of data uncompressed, we would need 178 megabytes of data. So even the fastest internet today could not handle that. And this is just for full HD. I mean, if you're on Netflix, a lot of the new stuff is in ultra HD, right? 4K. So that's, take this problem and it makes it a lot worse. Okay. So, the idea would be is that we have a need for compression in the streaming world, which we see all the time. But really for almost anything, if you're downloading a large file, and there's a way to make the download of the transport portion of that faster by making the file smaller, and then having a way of decompressing it on the back end. If that's all stuff that can happen, this is a positive thing. Okay. So we have something called Huffman coding, and actually it'll probably be, let's see how I want to do this. If there's some good pictures, we can go. All right, so we'll come back to this here in a few minutes. All right, so the idea of Huffman coding is, and so we'll look at this like kind of at the full algorithm level, and then we'll dig in a little bit closer because we're ultimately going to do this. But the idea of Huffman coding is this is one possible way of doing, typically we think about this as text-based compression, where text-based compression does not necessarily rely on compressing bytes and bits. You could do it with that, but there's probably other compression techniques that would be better for that. For example, if you think about Netflix and their streaming algorithm, they're probably not using Huffman coding for compressing 4K video. But this is a relatively easy to understand process. But when you go to compress some text, you start off by creating a table that has the frequency of all the different items. So here's kind of the high level algorithm of it, but let's just look down here. So we create a frequency. So let's say we have the character A, and the character A occurs 5 times in the text. Character B occurs 9 times, C 12 times, D 13, E 16, F 45 times. So you have this table of the frequency of all of those characters. Now that's specific to the message that you are compressing, which means that if you're compressing it using that frequency table, that's because you knew what the message was before you were compressing, then the dude who's decompressing at the other end is going to need that frequency table in order to form the Huffman codes in order to decompress the text. That makes some sense? What, can you pull that shot real quick? Thanks. So you're gonna need that in order to decompress the thing. So one of the things you're gonna need to do is send this frequency table. Now, on top of that, this isn't overly secure, right? You know, because now we're like, hey, look, here's all the information you need to decompress it. But compression does not necessarily say anything about security. That's encryption. You can encrypt compressed stuff, then decrypt it, then decompress it, right? So, you know, two separate worlds, let's say. All right, so you have your frequency of your original message. Let's see, okay, so here's our original examples. So we have A's, B's, C's, and D's. Okay, so we see that A occurs 4 times, B occurs 3 times, C occurs twice, and D occurs once. So that is effectively our table, our frequency table. So now each of those items is going to be a leaf node. So first determines the frequencies of each item. We just did that. Okay. Each item is then a leaf node in a tree. The pair of nodes yielding the lowest sum is found and merged into a new node formed with that sum. So if we look at this, we have A is 4, B is 3. To compress your text, you're going to be following kind of like GPS to get to your most often found character here from the top of the tree takes no effort, 0 down to go to 0. It takes a little bit more effort to get to the right hand side where you have more of your characters. That's where your 1 comes in. Then you drop down to your 6, and I'm going to show you examples of codes on the flip side. So it's easier to get down to the B, the next most frequent character. So this would be 0, 0 gets you to a B. I'm sorry, 1, 0 gets you to the B. So this is the Huffman code for a B. 0 gets you to an A. 1, 0 gets you to a B. 1, 1, 0 gets you to a C. 1, 1, 1 gets you to a D. So these are the Huffman codes for those particular values. All right. Okay, we're going to say that's good enough for this picture. So now let me take you through a process. So we have we're talking about doing this as a minimum heap, but this is the binary tree version of a heap. So we've kind of already seen this. Remember a heap, oh, hold on, get waiting room people. Remember that a heap is an implementation of a priority queue. So the reason we use a heap for this is that the most commonly used things are the highest priority, and the least commonly are the lowest priority. Get down to our actually, do I want to use, yeah, we'll use C++ for this. All right, so our goal is to get Huffman codes. That is things that we can use to replace each of the characters as we go through those characters. So in our example here, if we have A, B, C, D, E, and F, these are the Huffman codes for those particular guys. Now, if you then gave it a string consisting of these particular things, so this is like your original, I don't know, rubric for doing this in coding. So we know that if you have these Huffman codes, if you have your array and your frequency, these 2 pieces of information give you everything you need in order to generate Huffman codes. Now, once you have the Huffman codes, you can use that to compress or decompress any text that involves those particular symbols. The text has to be made up of A's, B's, C's, D's, E's, and F's. But you can use it for anyone as long as you accept that these are the Huffman codes for A's, for B's, for C's, so on and so forth. Okay, so in main here, we have this is our frequency table. Those are all our characters. That's how often they appear in our example here. Okay. Then we're going to call our Huffman codes function, pass and get the frequency table. So that's this guy right here. A little bit bigger, right? All right, so these are our list of characters. Here's the list of frequencies. All right, so now we're doing this as a tree, but we're not going to focus too much on the tree here as we walk through the algorithm. We just know that ultimately we're going to be producing something along these lines. All right, and the way we traverse this tree is relative to how we can compress the data. All right. So we're creating a minimum heap. So a min heap says that the most important thing is the thing that's the smallest value, right? The lowest priority as opposed to a maximum heap where the maximum value is at the top. All right, so we're going to go through all of the elements. And notice we're building something called a min heap node, but we're passing it each individual character along with the frequency for that character. So a min heap node, this guy up here, when we build it, here's our constructor for it. We're passing it a single char and then an unsigned integer frequency. And it's going to build our tree thing. Again, we don't have to worry about that for this exact moment. All right, so what are we getting in here? We're getting a heap node that associates a particular character with a frequency, and we're pushing it onto our min heap. Now, min heap is going to have that job of making sure that the minimum value is the highest priority, since this guy is a priority queue. All right, so now we're doing that for all of our frequency tables. So this loads our frequency table into a heap data structure, ultimately producing something that kind of sort of looks like this. Okay, so now, so while the heap still has stuff in it, we can go through and we see what our output here is we get our Huffman codes for this guy. So as long as our heap still has stuff in it, we grab the left from the heap top, remove that from the top. The right becomes the new heap top. So ultimately what we're doing here is we're grabbing the left from this guy, preserving it. The right becomes the new top. So this is the new top value, with a min heap being the smallest value here is the most important value. It's the most costly to get down to it. Part of the reason for that in Huffman coding is if we have characters that occur very often, we want to represent those characters in the smallest footprint possible, right? We do need to be able to uniquely, because remember the goal here is to compress, is to make it smaller. We do need to be able to accurately differentiate in this example between A's, B's, C's, and D's. So those need to be unique values in order for us to change the way they're representing and then flip it back later on. But if we have an A occurring very, very often, it's in our best interest to have that A be represented as a single zero. Whereas something that rarely occurs, we can have that being represented as a larger value. Now, keep in mind, we're looking at this in binary here, but we can so that's the way it would ultimately be represented. But let me ask you this. How big, what's the data footprint of this guy right here? So this is what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 characters there. What's the data footprint of those 10 characters? How big, how much memory do we need to represent those 10 characters? Let's just say we're talking about C++. Remember, our goal here is to shrink, right? We're compressing. How big is a single char in C++? You can give me the Java answer too. The Java answer is a larger value. But how big? Go ahead. A byte. Okay, because C++ represents chars using ASCII. Java represents chars using Unicode. So it's actually 2 bytes, 16 bits. Unicode is 65,536 unique characters. ASCII is only, actually, true ASCII is 128 unique characters, but it's still represented as a byte, so it's 0 to 255 are your possible placeholders in ASCII. So we're going to have 1 byte representing these guys. And how many did I say there are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means we have 80 bits, right? 10 bytes, 80 bits. So that's 80 zeros and ones if we were to write that. So let me kind of, we'll do this slide here. Oh. So this is AA, BBB, AA, CCD. All right, and we decided the Huffman codes for this is A is 0, B is 10, C is 110. All right, we were just counting. So this is 0, 2, 0, 1, 2. So this is a 3, and this is a 1's place, 2's place, 4's place. So that's a 7. 1's place, 2's place, 4's place. This is actually a 6, so on and so forth. But it's a bit representation. So we don't need to count this as the number, what number this represents. We just have to say that A's are represented by a single bit of 0. A B is represented by 2 bits of 1, 0. A C is represented by 3 bits, 1, 1, 0. So on and so forth. All right, so A is 0. B is equal to 1, 0. C is equal to 1, 1, 0. D is equal to 1, 1, 1. Okay, so we know that original is 80 bits. 10 bytes. That's how big the original value is. If we go and we rewrite this using Huffman's codes, this would be 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1. So that's 3, 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 total bits. So 23, 24% of the original size. We compressed it because we were able to represent this string of characters in a smaller footprint. Make some sense? Now, I think in this particular example, if we flip this around, let's say that this was, actually, let me do it as a, I'm going to do it as a separate slide. if we do it as a max heap, which is not the way it works. I just want to kind of show the difference. We saw with this guy roughly a 24% compression. We had 19 bits compared to, actually it's not 24, it's 76%, right? It's 24% of the original size. So a 76%, the result is 24% of the original data size. We're going to say that's pretty good. Now, if we flip this around, let's just do it in the worst possible way. Related to Huffman. So an A is 111, a B is 110, a C is 10, and a D is 0. So now, if we go and we replace this, we have 111, 111, 110, 110, 111, 111, and then a D, right? 0. That's 1, that's 3, 6, 9, 12, 15, 18, 19. It's still 19 bits total, right? Because they came out to the same number of bits. It's a bad example. Oh, I didn't do the C's. AA, BB, no, I should have 3 A's. AAA, BB, AA. Oh, and then C is 10, 10, and then 0. So this is 2, 3, 4, 5, 6, 7. 7 times 3 is 21, 23, 25, 26. So that's 26 bits as opposed to 80 bits. Still did relatively okay, compression wise. We still represented it as a smaller value. Now that's not a promise, but the idea is that what is compression? Compression says that we're going to represent one thing as something else. We're going to replace something in such a way that it is smaller. And when we're dealing specifically with text and computers, the way computers represent text is in bytes or words, double bytes for Unicode, which would be a more common way of doing it. So the reality is if we were doing this in modern day text where we support lots more characters, we would really say that the amount of data that's being sent for this guy is 160 bits, twice the number of bits to send this in Unicode format as opposed to ASCII format. But every single character would be 16 bits big. So as long as we can represent it in less than 16 bits, we're shrinking it. We're winning, right? Are we guaranteed to replace a character in less than 16 bits? So let me see. That's the if every single character is guaranteed in normal Unicode, is guaranteed to be 16 bits. Or we could even use ASCII. Numbers would be less scary. So if we say every single character in ASCII is guaranteed to be 8 bits, uncompressed, they're all guaranteed to be 8 bits. Because that's what the ASCII table is. Isn't the ASCII table kind of like the Huffman codes? It says an A is this, a B is this, a C is this, a D is this, right? It has a number associated with it. Okay, that's just a lookup table. But we say that every single one of those guys is going to be represented as 8 bits. Why 8 bits? Well, because they want to be able to represent 2 to the 8th unique characters. It doesn't matter what the math is for A. right? It doesn't matter that A's number is a certain number and B's number is another number and C's number is another number. It is helpful that in ASCII, those guys are right next to each other, because then you can kind of do math relative to lowercase a versus uppercase a, where they live in the table. So it's nice to have them in continuous areas. But if they had just decided that a lowercase a was ASCII 0, which it's not, but if they had decided that, that's not a big deal, okay? All they did is they said with ASCII, we have 256 unique values that we can represent in 8 bits. That's what 8 bits lets us do. There are 256 unique ways of writing 8 bits. And we can have each of those unique ways representing a single thing. All right. So with a string that's uncompressed, and we're going to say it's ASCII text, we are 100% guaranteed that every single character is always the size of is always 8 bits. That's guaranteed, right? What's the largest value for a Huffman code? These Huffman codes were built relative to each other, right? So the question I'm asking here, is it always better if ASCII characters are always 8 bits big, regardless of how often they occur? It's kind of the kicker here. Doesn't matter how often they occur, they're 8 bits. Always. Is, let's say, does Huffman coding always reduce the size of a file? What is the maximum size of a Huffman code? Now we saw here, go back to my chart, that these codes got bigger and bigger, they got longer as elements became less common, right? So we definitely erred on the side of we want to represent the things that occurred most often in the smaller piece. So we're gaining the most compression in those situations, right? If A occurred 10,000 times in our string, and we're representing each of those guys as a 0, a single bit, we're compressing that 8 times. It's an 800% compression, right? Pretty solid. Especially if that's the thing that happens most often. So a majority of the document, relatively speaking, the most common characters in the document are compressed the most. The next most common elements are very compressed the next most. Only the least things are lightly compressed. So does Huffman coding always work? Yes, it's always going to make it better, but it doesn't necessarily guarantee us a certain level of compression. But what's the largest Huffman code we could possibly have? What would be the scenario that would give us the largest Huffman codes? Go ahead. Yeah, so if we had all 256 characters, right? And maybe the worst case would be they all occur exactly once. So if we don't have a differentiating factor between, so worst case, we have all 256 ASCII characters, each occurring one time. We still need to uniquely represent each of those characters. Will Huffman coding help with this? So in a worst case scenario, if I have literally every single ASCII character occur exactly one time, which would be unlikely, right? That's a very specific email that's being sent, right? But possible, it is possible that you're trying to send the ASCII table one character at a time. So would Huffman coding help with this? We're not going to go through the exercise of actually building the table for the Huffman frequency table for these guys, but would it actually make it smaller? Is it guaranteed with Huffman codes that we're going to end up with a unique code for representing every single character that's in our input string? That's guaranteed, right? The whole purpose of Huffman coding is we will replace a character with a code, with the hope that a code ends up being smaller than the 8-bit representation of the character often, with the super promise of the most common characters will be represented in the smallest number of replacements, and we catch up. But in the worst case scenario, when we have all 256 ASCII characters, each showing up exactly one time, so we don't really have a most common occurrence character, we will have a Huffman code for every single character in the 256. Will this be any better? In ASCII, every single character is represented as 8 bits. That's the ASCII mapping. So there are 2 to the 8th unique characters. In Huffman, we already saw that we can represent a single character as a 0. Maybe an A is a 0. A B is a 1-0. A C is a 1-1. A D is a 0, is a 1-0-0. 1-0-1, so on and so forth. Do we actually shrink that ASCII table if we have every single character? Do we actually shrink it down using Huffman coding? Why or why not? Is any ASCII character a single bit? Or are they all 8 bits? 100% of them are 8 bits, right? Even though if we look at the ASCII table, we look at the ASCII table, we have this is 0, this is 1, all the way up to I mentioned earlier that there's actually only 128 unique ASCII characters, but since it's 8 bits, you could technically say it's only 7 bits, but we have extended ASCII. This gets us up to 255. And that's where you get like weird, like playing cards and symbols and stupid stuff. But, you know, for all intents and purposes, we've been talking about it as 8 bits. So we get 256 unique characters. But every single one of these characters, this guy number 26 right here, 26 is represented as 8 bits. Why is that? Why is ASCII guaranteed to be 8 bits? And why is the next level up, Unicode, why is that guaranteed to be 16 bits? Why can't I say, well, since this guy's only a 0, why can't I just represent that as 1 bit? And the 2, you know, why can't I represent that as 2 bits? Because you can write the number 2, the decimal 2 in 2 bits. I don't even need to get up to 8 bits until after I hit 120, when I get to 128. The first ASCII character that would need 8 bits to represent the number would be the 128. That's a 1 with 0 sevens after it, right? Why is ASCII represented always as 8 bits? Go ahead. Okay. Okay, so if we're reading in a string, if we're trying to send a string over the internet or from one part of the computer to another part of the computer, we're trying to send hello across the computer. And I'm giving it a series of bits because the way we represent characters, the way we represent anything in computers is numbers, right? So I'm giving it a series of bits. I give it to the thing in 8-bit chunks so that the destination knows to divide it, right? It needs to know to divide those things up. So it knows that, okay, every 8 bits, you're talking about a different char. Even though for many of those, for half of them, you didn't need 8 bits to represent it, right? Guaranteed. Half of these characters, the original Unicode or original ASCII character set was only 7 bits. So extended ASCII, half of them can be represented in less than 8 bits. But we're guaranteeing that they're all 8 bits because we need to treat every single char equally if we're going to represent it as numbers, but also translate it back into a character to show on the screen for outputting something for human consumption. Okay, so the way data was represented needed to be consistent at the cost of more data, right? Our original null value here was a 0, and we decided, okay, well, this guy is going to be represented as 8 zeros, which is the decimal version of 0. A lowercase a or uppercase a right here. Hold on, that's actually hexadecimal values. That's a 10. Let me get to our A's over here. Here's an uppercase A that's value 65. So 64, 1s, 2s, 4s, 8s, 16s, 32s, 64ths is, what am I doing that right? 1s, 2s, 4s, 8s, 16s, 32s, 64s. It's not going to take 7 bits. It's going to take 7 bits to represent. So that's a 2, that's a 4, 8, 16, 32, 64, 128, 256, but this is 8 bits. 3, 4, 5, 6, 7, 8. So by 255 is all ones. That's 0 to 255. So that is 64. So that is 1, 2, 3, 4, 5, 6, 7 bits. So we can do 7 bits for 64 all the way up to 127. Because the number 127 is that. 7 ones is 127. 128 is that. 255 is that. All right, so even going to 64, we still needed 7 bits in order to represent 64. So the character 65A is that. So in ASCII, that is the binary version of a capital A. Capital B is that, C is that, so on and so forth. All right, so we needed 7 bits to represent those guys, and they are sitting next to each other. So we can certainly say, if we look at this from the perspective of what if our text is only made up of lower and uppercase characters, then Huffman codes really help, right? Because we're starting off at 7 bits. We actually start off and finish off at 7 bits for representing the alphabet. Okay, because the entire alphabet here starts off at 65, goes all the way up to 122. All of that is housed inside of a 7-bit space. All those numbers can be represented as 7 bits. So any way you cut it, if we had characters that did occur less often, they would be smaller than 7 bits, because the least common character in Huffman will always be a 0. The next one will always be a 10. The next one will always be a 11. The next one will always be a 100. So on and so forth. Those are the unique Huffman codes we might be dealing with. So if we had all 256 ASCII characters occurring 1 time each, would that still be better than the amount of data that it took to represent 256 ASCII characters? 256 ASCII characters is 2048 bits. It's a lot of bits. Well, how many would it be in Huffman codes? So how much data will that take in Huffman coding? We have 256 ASCII characters, each occurring exactly 1 time. What do you think? Well, for 128 of those, we're going to have 8 bits. Won't that be the largest Huffman code? Will we ever have a Huffman code if we're dealing with ASCII? Will we ever have one that's larger than 8 bits? But the job of a Huffman code is to uniquely identify every single character, which means that we would end up having a tree where's my tree? We'd end up having a pretty big tree here that goes through the entire alphabet, right? So if you follow this, and well, we'd have 256 of these guys, what would it end up looking like? The Huffman code for this guy was 111. Why? Because we went to the right, we went to the right, we went to the right. That gave me 111. Well, that only took us to the 4th character. So if I had 256 characters, how many ones would we have to get to that guy? 255. So Huffman codes don't fill up the entire bit space. Huffman codes are reliant on us walking a min heap. Things look pretty good when we're sitting with here, and they would look pretty good if we're dealing with Unicode character or dealing with just the alphabetic characters. But with just 4 unique characters, we had 4 different ways of representing them, but these are not counting, right? This is a 0. This is a 2. This is a 6. Right, so 0's one place, 1's place, 2's actually, this is a 3. So 0, 2, 3. This is 1's, 2's, 4's, 4, 5, 6, 7. This is a 7. So these guys are not counting sequentially. They're unique representations of each of those chars, but they're not counting sequentially. So because I'm representing this in a heap, in order to have 256 unique characters here, the far right character would be a 1, then 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 a 1. Keep taking the right path all the way down until my, in this example, the least common character, which in our worst case example is every character occurs one time. So somebody would have to be the loser. He would be the else to everything else. You know, does this occur less often than this one, less often than this one, less often than this one? They're all going to be equal to each other. So instead of the less than, it would be less than or equal to. Somebody will end up being the loser. Doesn't really matter who it is since they all occur one time. But that far right character would be represented as 256 ones. A lot of ones. What about the guy just less than him? He would be represented as 255 ones with a 0 at the end. What about the guy next to him? Just keep trickling down. So you'd have a whole bunch of those characters, instead of being represented as 8 bits, you'd have them represented as 256 bits. Oh, now we're going in the wrong direction. What do you think? What's the math going to end up being? It's no longer clearly less, right? Math probably comes out to being identical. The same bit space would be taken up if every single character existed. So that means that the thing that we're compressing takes up a different amount of space depending on our own luck. What did the original data look like? Now we can say that emails and things like that we might write might typically be filled up with a very small subset of the ASCII character set, which means that a high percentage of the time, Huffman coding is going to drastically shrink our data, right? Probably very much so if you start looking at statistics of, you know, I don't know exactly what the most common characters are, but somewhere there's going to be the data science behind this where it says, you know, the letter B occurs more often than any other character in a book, something like that. So somewhere there's a frequency table that says how often these different characters, and there'll be some kind of like, I've seen these for like words, like the word is occurs more often than any other word, and the word and occurs very, very often. But the word plethora probably is not a very common word that's just going to appear in the text. So the same thing's going to be true with letters. So the idea that our most commonly occurring letters should have the smallest footprint. So Huffman encoding should be pretty good most of the time. That makes some sense? Okay, so we're actually not going to implement Huffman codes. If we were going to, we would have done it when we did our heap. We actually didn't finish our heap completely. We just looked at the last of it. But we would end up with, what's the purpose of Huffman codes? Huffman codes are saying, let's represent our most commonly used characters in some text with the smallest footprint number possible. We'll call it simple compression. All right, we're going to come back Wednesday. We're going to look at one last algorithm. Depending, I probably won't have you implement it for Friday. So on Friday, we'll talk about the exam. The exam is going to be up, I'll probably put it up Sunday night, and you just have to take it sometime during the week of finals week until Friday at midnight, so I can grade it over the weekend. But I'll announce whatever the official time is for when our exam will be. I'll make sure that I'm sitting in front of a computer. So if you have real-time questions about the exam when we're when you would have been taking it in class, I'll be available. But we'll talk about that on Friday. All right, questions, comments, concerns, bribes. All right, I'll see everybody on Wednesday. Oh, Zipf's Law apparently is what it's called. That's going to be that idea of certain characters occur the most often, I'm guessing. Let me look it up. Oh yeah, that's the frequency of words. So I'm sure there's the equivalent for characters. Somebody's done the math, I'm sure. Or has a decent estimate of it. All right, I'll see everybody on Wednesday.